Is nuclear fusion. What is it? I'll let an MIT professor explain it to a child. Take a look.
My son is 5 years old, and he asked me what kind of science I do. And I said, fusion. And I said, I put a star in a jar. Does that make sense? That's a good answer, because it sounds a little ridiculous, right? How can we put a star in a jar? Well, we're not actually going to put the sun, which is a star, inside a jar, but instead we're going to take the same kind of material that the sun is made out of, and we're going to hold it for a really long time in some kind of container. So fusion is about bringing things together.
Okay, so put some sun stuff in a star. Ann White joins us now. She is a professor of engineering at MIT. Thank you so very much for joining us. Now that we've got like the beginning of the definition of nuclear fusion, can you take us to the next step? How do we get that star in a jar?
Absolutely. So thank you so much for having me here. How do we actually get the star in a jar? Well, we have to start with the right kind of fuel for a fusion system. And that right kind of fuel is a plasma. And if we're going to make a plasma, we've got to start by taking the right kind of gas. And so in this case, we're going to take a gas made up of isotopes of hydrogen. Isotopes are just heavier versions of hydrogen. They're just a different, flavor of the element, if you will. And we need to take that gas and we need to put a little bit of it into the right kind of container. And that container might be using strong magnetic fields to hold this plasma in place, or it might be using compression, like at the National Ignition Facility. So we're going to take that gas and put it into this container and heat it up to hundreds of millions of degrees. And at that point, we are controlling a plasma, and we're able to control the plasma, push and pull it, because plasmas, unlike neutral gases, can conduct electricity. And one of the most striking examples of this that a lot of your viewers might be familiar with would be a lightning bolt. That is a form of a plasma. It is an ionized gas.
Sounds super, super easy, and yet so difficult, especially when you consider the energy going in versus the energy coming out. And then all of a sudden, we're starting to see some headlines promising a major breakthrough. Where do you think we actually stand right now when it comes to nuclear fusion being something that is sustainable and that we can use?
We're actually extraordinarily close. I would argue closer than we've ever been before. We're at a stage now where scientists are able to understand, calculate, and predict pretty much all of the complex dynamic processes that happen in a variety of different fusion plasmas. You combine that with a great deal of interest from private industry and private money getting invested into a wide range of different ways of confining that plasma and ultimately converting it into a net energy system and a net electricity system. And you've got the right kind of mix for some really tremendous breakthroughs to happen on a very fast path.
Not to oversimplify here, because that's what journalists do, not scientists, but it sounds like what you're saying is we have all the modeling that we need and all the computing power that we need to figure this stuff out. Now we just have to start lighting some fires in a very safe and contained way to test it out. Is that right?
It's right, and it's not just my opinion. There's a lot of consensus reports that have been written by scientists. I'll point especially to our own country in the United States, which say that we are ready to do this. And several years of our community planning and thinking together about really why we want to do this and why it's the right moment to do this has culminated in a bold decadal vision from this administration at the White House to say, well, let's do it then. Let's build a fusion pilot plant. Let's build a system at scale that will demonstrate how we get the electricity produced from fusion. And so this gets down to a lot of really taking what we understand about the plasma physics and combining it with the engineering. To come back to a great question you asked at the very beginning, what does it take to get to that pilot plant? Well, we've got to get this plasma to the right condition so that we are producing enough fusion products in the form of very, very energetic neutrons, which are carrying so much kinetic energy. They're moving at 17% the speed of light. They're moving at 30,000 miles per second. We need to convert that kinetic energy into heat and then ultimately convert that heat into electricity. So again, we understand, the basic steps to do this, but actually putting it all together in a package that is functioning exactly the way we want it in a very reproducible manner is still a big challenge. And there's still a lot of sort of research and development to do along that path. But again, the key is we can accelerate it.
Okay, last question, very quickly. Prediction, this is going to happen the next 5 years, next 10 years, next 20 years? What do you think?
I think that we're going to see a lot of really exciting results happening in just the next 5 years. And again, if we can sort of live up to the bold decadal vision, you will see a demonstration of electricity in about 10 years. And sort of how we go from that sort of basic science, basic research and development, translating that to a working power plant that utilities are going to want to buy and want to put that clean electricity on the grid. That's an interesting question. And so I think that we'll be optimistic and we'll say, let's stick with the bold decadal vision, and we'll say 10 years, let's see electricity from fusion demonstrated.
Professor White, that sounds like a very scientifically sound answer. Thank you so very much for joining us.